Hello everyone. Um, in the last video we started to talk about ordering of elements. So we just so that we quickly recap on what we've said. So there is something called order of a group or cardinality, and that actually means the size of that set, the size or the number of elements in that group. But when we say order of elements, then we're talking about where are they positioned in the set. So according so we've talked about equivalence relations, and we know that to suffice an equivalence relation, or in that sense, the in order for the group to suffice shared property, there has to be three main properties. Um, so it has to be symmetric, it has to be transitive, and it has to be reflexive. So those three properties, if they suffice, then you have an equivalence relation. However, if you're talking about ordering, one of the properties is handled differently. So you still have reflexivity and you still have transitivity, but you lack symmetric, the symmetric property or the symmetric property. And we can look at so we've actually started doing some other things here, and if we can just quickly go through this, because I just feel like we need to do more of this, because apparently Zon's lemma, which we were supposed to talk about the last time, is quite important in our journey. So anyway, so let's keep on going with the order theory. So I've got a paper and a pen with me, so it's like I just feel like it's easier for me to fully grasp what I'm reading if I'm writing down the important stuff. It might be slow, but it's easier. It makes things a lot faster later on in the long term, though. So in the order theory, the main so in order theory, the main unit is basically called the binary relation. Binary relation, it just means that one-to-one. Can we can see this in the wiki here, that over two sets A and B is a set of ordered pairs A, B, consisting of elements A of A and elements B of B. In short, it's a subset of the Cartesian product A, B. It encodes the information of relation. An element A is related to an element B if and only if the pair A, B belongs to the set. So that's primarily what the binary relationship means, the Cartesian product. So the Cartesian product with a condition. So the condition is basically, start a notepad. So we have the order binary relation is the Cartesian product. So X B, the condition of both belong. So the binary relation of the sets. But which set does it belong to? You know that is over two sets, but which set does it belong to? I mean, the end result, does it belong to the Cartesian product? Okay, so binary relation over two sets A and B is a set of ordered pairs A, B consisting of elements of, in short, it's a subset of the Cartesian product A. It encodes the information of relation. An element A is related to an element B if and only if the pair AB belongs to the set. But which set is it? It divides the relation over the set of primary numbers P and the set of integers C, in which prime P is related to each integer Z that is a multiple of P. But another integer that is not a multiple of P. In this relation, the prime 2 is related to the numbers that include but not 1 or 9, and the prime 3 is related to the numbers but not, yeah. Binary relations are used in many branches. To the larger set, I think belongs to the domain, maybe. So the domain. Yeah, I'll just keep it out. This seems to be the closest definition we could get. So basically, you're talking about A and B's, and there's just some sort of connection between them. So a binary relation over A and B is an element in the power set, since the later set is ordered by inclusion. Alright, let's go with Stanford. Problem set. Okay, that's not. I just explored the graph as a way of studying relations between two objects. However, graphs are not the only formalism we can use to do this. Relationships. We have seen different types of relationships between sets. Yeah. Study their properties. Intuitively speaking, a binary relation over set A is some relation R for every xy belongs to A. This relation Y is either true or false. So this could be a binary relation. It's basically any kind of relationship is considered a binary relation. So in this case, you have 4 and 4, and you have 1, 4, you have 2, 4, then you have 1, 2, 2, 2, 3, 3. So these are all relations. A divides B over the set. 1, 2, 3, 4. Okay. You can visualize a binary relation R over set A as the graph. Oh man. Okay, so these are all like fancy stuff. not fancy stuff, but we're saying, what if we try to do this video?
Hello, I'm Professor Von Schmohawk, and welcome to YU. We have seen how ordered pairs can be graphically represented as points in a plane using Cartesian coordinates. As we will see later in this lecture, this set of ordered pairs is an example of a binary relation. A binary relation relates various elements of one set to elements of another set. For example, let's say that set A contains Tarzan, Jane, and Boy, and set B contains oranges, apples, and bananas. Now, how might the elements of these two sets be related? One possible relation between these people and fruit would be that certain people in set A like certain fruit in set B. For instance, let's say that Tarzan likes oranges, Boy likes apples and bananas, and Jane likes oranges, apples, and bananas. Instead of drawing multiple arrows from a single person, we could represent this relation by a collection of individual arrows, each connecting one person to one fruit. Or, instead of drawing arrows, we could represent each association between a person and a fruit as an ordered pair. In each ordered pair, the first element is a person from set A, and the second element is one fruit from set B which that person likes. We call these pairs of elements ordered since the two elements cannot be swapped without changing the meaning of the relation.
Yes, so antisymmetric.
For example, Tarzan likes oranges, but oranges don't necessarily like Tarzan.
So if you basically suffice the first one, you're saying that it's a symmetric relation. In that sense, you have Tarzan liking an orange and orange liking Tarzan back. So that's a symmetric relation. But it wouldn't make sense saying the orange likes Tarzan. So antisymmetric, and that's what ordered pairs are. You cannot switch them. It's like you need to preserve the order. Now that makes perfect sense. That's what order is all about. You have to have. So you could have like Tarzan or Tarzan or orange, and then you could go like if Tarzan likes orange, and orange likes I don't know, Boy, then Tarzan likes I don't know, something like that.
This collection of ordered pairs symbolizes associations from members of one set to members of another set. We call the set that contains these ordered pairs a binary relation.
So that's a binary relation.
Let's name this set of ordered pairs L. So we say that L is a binary relation from set A to set B. Each ordered pair that's a member of set L makes a statement about how one person in set A is related to one fruit in set B. A mathematician would say that this ordered pair makes the statement Jane is L related to oranges. Or in plain English, Jane likes oranges. You may recall from previous lectures that the Cartesian product of two sets is also a set of ordered pairs. Unlike relation L, the Cartesian product contains every possible ordered pair which can be created, where the first element of the ordered pair is a member of set A and the second element is a member of B. The Cartesian product of sets A and B therefore contains all 9 possible ordered pairs, as opposed to the 6 contained in relation L. Of course, everyone in set A could have liked every fruit in set B. In that case, relation L would have been the same as the Cartesian product. On the other hand, it might be that nobody in set A likes fruit. In that case, relation L would be the empty set. So a binary relation from one set to another is always a subset of their Cartesian product, since it can contain as many as all or as few as none of the ordered pairs in the Cartesian product. Binary relations don't necessarily have to involve two different sets. A binary relation can exist between members of the same set. For example, we could take two copies of set A, which contains Tarzan, Jane, and Boy, and draw arrows from each member to every member who is shorter. So this relation is represented by three ordered pairs, where the first element of each ordered pair is the taller person, and the second element is the shorter person. Let's call this relation T. Since both sets involved in this binary relation are the same set, A, we call T a binary relation on set A. Each ordered pair in set T makes a statement about how one person in set A is related to a person in the same set. This ordered pair makes the statement Tarzan is T related to Jane, or in plain English, Tarzan is taller than Jane. As we saw, a binary relation from one set to another is a subset of their Cartesian product. So T is a subset of the Cartesian product of set A with itself, or A squared. A squared contains all 9 possible ordered pairs which can be created from the 3 members of set A. If we eliminate all the ordered pairs of A squared, whose first element is not a person taller than the second element, we get relation T. In the beginning of this lecture, we showed a group of points in the xy plane and said that this is an example of a binary relation. So what are the two sets in this binary relation, and how are they related? As we saw, a point on the xy plane is a visual representation of an ordered pair of real numbers, where the first element of the ordered pair corresponds to a number on the x-axis, and the second element corresponds to a number on the y-axis.
Flipping them will change the meaning.
So the ordered pair relates one member of the set of real numbers represented by the x-axis to one member of the set of real numbers represented by the y-axis. A set consisting of this ordered pair would thus be a binary relation from one set of real numbers to the other,
Real numbers.
and the corresponding point on the xy plane is a visual representation of this relation.
So it's a subset.
Of course, a binary relation can include more than one ordered pair. So the group of points we showed in the beginning is a visual representation of a binary relation on R, the set of real numbers. As we saw, a binary relation between two sets is a subset of their Cartesian product.
X and Y.
So this binary relation is a subset of the Cartesian product of the set of real numbers with itself, R2, which consists of every point in the xy plane. In the next lecture, we will introduce two important sets in any binary relation, called the domain and the range of the relation.
I already know that, so this is really interesting. This is a nice set of
Hello!
it's pretty nice. Good. Let's go with the so this is a really nice set of videos. I mean, it just explains most of the concepts we need to know about. So we've done algebra 12. We already know this. So what are we left with then? Notation. Cartesian product ordered pairs.
Hello! In the previous lectures, we described bounded and unbounded intervals. Bounded intervals are limited by their endpoints to a finite length on the number line. Bounded intervals can be closed, open, closed. Unbounded intervals and right closed or open intervals. However, not all intervals are proper. It is possible for an interval to include only one point or no points. If the left and right endpoints of a closed interval are the same number, then the interval is called a degenerate interval and represents a single point on the number line. So a degenerate interval is a set which contains one real number.
I should write this down.
On the other hand, if both endpoints of an open interval are the same, then that interval contains no points. So this interval represents the empty set. So this interval represents the empty interval contains open interval are the same, then that interval contains no points. So this interval represents the empty set. When we first introduced interval notation, we said that an interval was a special type of set consisting of a continuous span of one real number. On the other hand, if both in number line, interval is called a degenerate interval and represents a single point on the number line. So a degenerate interval is a set which contains one real number. On the other hand, if both endpoints of an open interval are the same, then that interval contains no points. So this interval represents the empty set. When we first introduced interval notation, we said that an interval was a special type of set consisting of a continuous span of numbers on the number line. Mathematicians call this property connectedness. Intervals are the connected sets of the number line. Even though a continuous span is intuitively easy to understand, a mathematician might define the concept of an interval in the following way. An interval is a set of real numbers with the property that any number that lies between two numbers in the set is also included in the set. So the key property of an interval is that no matter which two numbers we pick in the interval, every number between those two numbers must also be contained in the interval. Since the two numbers we pick can be as close as we like to the endpoints, no numbers which lie between the endpoints can be excluded from the interval. Therefore, every number between the two endpoints of an interval must be included in the interval. This property is true whether the endpoints are included in the interval or not included. For unbounded intervals, since one can pick two numbers arbitrarily far apart, all real numbers must be included in the interval. This definition is useful for testing if a set of real numbers can be represented by a single interval. For example, let's say that we have a set which consists of 0 and 2 and all numbers in between except the number 1. Using set builder notation, this would be the set of all numbers x such that x is greater than or equal to 0 and less than or equal to 2 and not equal to 1. But this set is not an interval. We know this because our definition for intervals says that every number that lies between any two numbers in the set must also be included in the set. However, the number 1 lies between numbers in this set. but is not included in the set. So this set cannot be described by a single interval. However, sometimes it is easier and more clear to describe regions of the number line like this set using interval notation. This can be accomplished by combining intervals. Since intervals are sets, we can use set operations to combine multiple intervals into one set. For example,
just to write down the notes, say, because primarily what's saying here is quite important
intervals
in the sense that, say for example, you have a set of x such that you have 0 is less than or equal to x less than or equal to 2, but x does not equal to 1. You see here that 1 is not
into one set. For example, we can take the left closed right open interval between 0 and 1 and the left open right closed interval between 1 and 2 and take their union to create the desired set. As another example, let's create one set containing all the numbers between 0 and 1 and between 2 and 3, but not including the endpoints. In set builder notation, this is the set of all numbers x such that x is greater than 0 and less than 1, or greater than 2 and less than 3. If we pick one number between 0 and 1 and a second number between 2 and 3, any number between 1 and 2 lies between these two numbers but is not a member of the set. Therefore, this set cannot be represented by a single interval. However, if we take the open interval between 0 and 1 and the open interval between 2 and 3, then the union of these two intervals creates the desired set. As a final example, let's create a set containing all real numbers except 0. In set builder notation, this is the set containing all numbers x not equal to 0. This set is not an interval, since if we pick any two numbers on either side of 0, both numbers are members of the set, but the number 0, which lies between these two numbers, is not a member of the set. We can represent this set using interval notation by taking the union of the left unbounded interval containing all numbers less than 0 and the right unbounded interval containing all numbers greater than 0. Intervals, which are neither empty nor degenerate, are said to be proper. As we have seen, all proper intervals contain more than one point. If an interval contains more than one point, it must contain intervals, which are neither empty nor degenerate, are said to be proper. As we have seen, all proper intervals contain more than one point. If an interval contains more than one point, it must contain an infinite number of points, since between any two distinct points on the number line, there are an infinite number of points. Therefore, all proper intervals are sets containing an infinite number of elements. So far, we have talked about sets of real numbers, and we have seen that these sets can be visualized using the number line. A line is a one-dimensional object, and the number line represents real numbers as points in this one-dimensional space. In the next lecture, we will examine mathematical objects which can be visualized as points in 2 or more dimensions. YU. In this lecture, we will introduce an important set operation called the Cartesian Product. This operation creates the framework on which the Cartesian coordinate system is based, allowing us to visualize mathematical relationships in 2 or more dimensions. So far, we have studied several set operations, including forming the union, the intersection, the relative complement, and the symmetric difference of sets.
Difference, yeah, that was the lovely one.
Each of these operations creates a new set containing some selection of elements from the operand sets.
Superset.
However, the Cartesian product is different. It doesn't take its elements from the operand sets. Instead, it combines elements from the operand sets to produce new elements. The Cartesian product of 2 sets creates elements called ordered pairs.
Yeah.
Forming the Cartesian product of 2 sets A and B involves creating ordered pairs as follows. We select an element from A and pair it with an element from B. The elements are enclosed in parentheses separated by a comma. This pair of elements forms an ordered pair, a single element created from the pair of operand elements. The order in which the elements of an ordered pair are listed is important.
Of course.
Unless 2 elements are the same, switching their order creates a different ordered pair. This is why the pair of elements is called ordered. To form the Cartesian product of 2 sets A and B, we create every possible ordered pair whose first element is from A and second element from B. Notice that each element of A is paired with every possible element of B. For example, the blue square from A forms ordered pairs with each of the triangles from B. The same is true for the green square and red square. Likewise, each element of B is paired with every possible element of A. The blue triangle from B forms ordered pairs with each of the squares from A. The same is true for the green triangle and red triangle. These 9 ordered pairs form a new set, the Cartesian product of A and B. This set contains every possible ordered pair whose first element is from set A and second element from set B.
So each ordered pair is actually a binary
The
relation.
Cartesian product is denoted using a symbol which looks like a multiplication symbol. We can display the ordered pairs of this Cartesian product in a 2-dimensional grid, where all the first elements are the same within any particular column, and all the second elements
like
are the same
columns
within
and
any
rows.
particular row. This grid of ordered pairs is a simple 2-dimensional coordinate system. A horizontal position in the grid can be chosen by specifying the color of square, and the vertical position by the color of triangle.
So something like X and Y's.
So by specifying the colors of square and triangle, we can locate any position within this 2-dimensional grid. Cartesian products can also be formed from more than 2 operand sets. For example, we can form the Cartesian product of 3 sets A, B, and C by repeatedly selecting one element from each set to form ordered triples. To create every possible ordered triple from 3 sets, we can start by forming the Cartesian product of sets A and B as we did before, and then choose one element from set C as a third element of the ordered triple. We then repeat this, each time choosing a different element from C. When we have done this for every element of C, every possible ordered triple will have been formed, whose first element is from set A, second element from set B, and third element from set C.
Notice that here he's saying that first element being A, second element being C, and third element being C. So the order here is very important. Otherwise, you'll have more combinations than what's already displayed. So for example, if the order wasn't really important, like as we've seen in equivalence relation, then you'll have to form all possible combinations from with B being the first one and C being the first one. So it's like you triple the results again. Like you'd have these three results done 3 times for each of the B's and C's being, B's being, so you'll have to form ABC and then BAC and then CBA, and then you have to also form ACB. So yeah, so that's why it's saying that the order is really important.
These ordered triples form the Cartesian product of A, B, and C. The ordered triples from the Cartesian product of 3 sets can be arranged in a 3-dimensional grid.
Yeah, so we need to write this. It's like super important. Cartesian product. Symmetric.
We can arrange the blocks so that all the first elements are the same in the left plane of blocks, the middle plane of blocks, and the right plane of blocks. For example, all the first elements in the left plane of blocks are blue squares, the middle plane are green squares, and the right plane are red squares. Likewise, the second elements are the same in each of the 3 horizontal planes. The second elements in the bottom plane are blue triangles. The middle plane are green or red triangles. Elements of the back, middle, and front planes. The third elements of the back plane are blue stars. The middle plane are green stars. This grid of ordered triples is a simple 3-dimensional coordinate system. A left to right position in the grid can be specified by the color of square, a bottom to top position by the color of triangle, and a back to front position by the color of star. So by specifying the colors of square, triangle, and star, we can locate any position within this 3-dimensional grid. We have seen that we can form the Cartesian product of 2 sets to create elements called ordered pairs, and we can form the Cartesian product of 3 sets to create elements called ordered triples. In fact, Cartesian products can be created from any number of sets. In general, the elements of a Cartesian product formed from n sets are referred to as n-tuples. Not only can Cartesian products be formed from any number of sets, but each operand set can contain any number of elements. The number of elements in the Cartesian product is equal to the number of elements in each operand set multiplied together. In the first example, we form the Cartesian product of 2 sets, each containing 3 elements. The resulting Cartesian product fit into a 3x3 grid containing 9 elements. When we form the Cartesian product of 3 sets, each containing 3 elements, the resulting Cartesian product fit into a 3x3x3 grid containing 27 elements.
What is it again?
n tuple to the number of elements
Centric.
in each operand set multiplied the Cartesian product of two sets, each containing 3 elements.
The 3D grid.
The resulting Cartesian product fit into a 3x3 grid
Not 3D.
containing 9 elements. When we form the Cartesian product of 3 sets, each containing 3 elements,
3D grid.
the resulting Cartesian product fit into a 3x3x3 grid containing 27 elements. If sets A, B, and C had contained 3, 4, and 5 elements, then the number of elements in their Cartesian product
3
would
by
be
4.
3 times 4 times 5, or 60 elements. The Cartesian product is named after the French mathematician and philosopher René Descartes. In the next lecture, we will see how Descartes' ideas led to the creation of the Cartesian coordinate system, uniting the subjects of algebra and geometry, and creating a revolutionary new way to visualize mathematics. And welcome to YU.
Rated badly.
We have seen that sets of real numbers can be visualized using the number line.
Apologies, I had paused the video and I've been going through all of this. So basically, what it says here is that the Cartesian product could be a Cartesian product to the same set by itself, so that's the a square. And if you try to plot the numbers into, like if it says here, assuming that instead of you taking a finite set of elements, you take an infinite set of elements, say the list of positive integers, the list of integers, that's z. If you take the Cartesian product of the set of integers, you'd basically create some sort of huge, like infinite set of infinite grid, right? And if you try to visualize that, you could think of each ordered pair as a point in a system, and that point in the system can be plotted in the x and y axes. Like as you can see here, each point corresponds to a point somewhere in the system, but assuming you went beyond and you decided to go for the left one being the x-axis and the right one being the y-axis. Now if you decided to go a step ahead and go for the R system, then it's like you form,
real numbers R with itself.
It's like you form this
We
space.
create a continuum of points which completely fill the plane.
Yeah, so that space, it could be dealt with just the same. And
it's called the Cartesian coordinate system.
This is what is called the Cartesian coordinate system.
Using ordered space. This system for visualizing ordered pairs of real numbers as points is called the Cartesian coordinate system.
Yeah. So, and then he was just saying that this guy is La Géométrie.
Geometry, published in 1630. Likewise, which describes geometric shapes by algebraic equations. Likewise, algebraic equations can be visualized as geometric shapes. This is possible because, as we will soon see, algebraic equations define sets of points which, when viewed in the Cartesian coordinate system, appear as shapes. The perpendicular number lines in the Cartesian coordinate system are referred to as axes. The horizontal and vertical axes are often called the x-axis and y-axis. Sometimes these two axes are referred to as the abscissa and the ordinate. The point where the axes meet represents the number 0 on each axis. This is called the origin of the coordinate system. The origin corresponds to the ordered pair 0, 0. The infinite plane containing the x and y axes is referred to as the Cartesian plane, or the xy plane. The axes divide the xy plane into 4 regions called quadrants.
was a
These
6.
are numbered from the first to fourth, starting with the upper right quadrant and continuing counterclockwise. The quadrants are usually denoted with Roman numerals. Many mathematicians prefer to draw number lines and axes with arrows pointing towards the positive direction only, indicating the direction of increasing value. We have seen that the number line corresponds to the set of real numbers R. So forming the Cartesian product of the set of real numbers with itself is equivalent to forming the Cartesian product of the number line with itself to form the Cartesian plane. And just as the number line consists of a continuum of points residing in one-dimensional space, where each point corresponds to a unique real number, the Cartesian plane consists of a continuum of points residing in two-dimensional space, where each point corresponds to a unique ordered pair of real numbers. Using a two-dimensional Cartesian coordinate system, we can graphically display sets of ordered pairs as groups of points in this space. Later, we will see how algebraic equations can describe infinite sets of points, which, when viewed in this system, appear as shapes in two dimensions.
This is lovely.
In the next lecture, we will see how a three-dimensional Cartesian coordinate system can be constructed, which will allow us to visualize sets of ordered triples in 3 dimensions.
Lovely.
And we'll construct ordered pairs of real numbers, or sets of these ordered pairs, as points in a plane. We did this by taking the Cartesian product of the one-dimensional number line with itself. To form the picture, we will construct a three-dimensional Cartesian coordinate system, which will allow us to display ordered triples of real numbers as points in three-dimensional space. The set of real numbers R can be thought of as corresponding to a continuum of points in one-dimensional space. It is this space which is represented by the number line. Each real number corresponds to a unique point in this one-dimensional space. We then created a two-dimensional Cartesian coordinate system by taking the Cartesian product of the set of real numbers with itself to form an infinite set of ordered pairs called R squared, or more commonly R2. R2 corresponds to a continuum of points in the two-dimensional space represented by the Cartesian plane, and each ordered pair of real numbers corresponds to a unique point in this two-dimensional space. However, we are not limited to forming Cartesian products of only two sets of real numbers. We can also form the Cartesian product of 3 sets to form the set R3. Just as the set R2 consists of ordered pairs whose elements can be any two real numbers, the set R3 consists of ordered triples whose elements can be any 3 real numbers. And just as the two-dimensional Cartesian plane was built from 2 number lines oriented perpendicular to each other, three-dimensional Cartesian space can be created by taking 3 number lines and orienting all 3 perpendicular to each other.
Nice.
These 3 axes are typically labeled X, Y, and Z, with the positive x-axis pointing out of the page, the positive y-axis pointing to the right, and the positive z-axis pointing up. Just as in 2 dimensions, the point where the 3 axes meet is called the origin. The origin corresponds to the ordered triple 0, 0, 0. The 3 axes
It's very important, I believe, visualizing
axes can be oriented in any way as long as all three axes are perpendicular to each other and they conform to what is called the right-hand rule. The right-hand rule states that if you align the thumb of your right hand pointing in the positive direction of the x-axis and your index finger pointing in the positive direction of the y-axis, then your middle finger should point in the positive direction of the z-axis. For example, we could arrange the axes so that the positive x-axis points to the right and positive y points up. In that case, the right-hand rule tells us that positive z must point out of the page. Or we could orient the axes with positive x pointing up, positive y pointing out of the page, and positive z pointing to the right. However, the typical orientation is with positive x pointing out, positive y pointing to the right, and positive z pointing up. In 3 dimensions, just as in 2 dimensions, the infinite plane containing the x and y axes is called the xy plane. Likewise, the y and z axes create the yz plane, and the x and z axes create the xz plane. These 3 planes divide the Cartesian space into 8 regions called octants. The octants are numbered 1 through 8 and are typically labeled using Roman numerals. Just as the 2-dimensional Cartesian coordinate system allows us to graphically display ordered pairs of real numbers as points on the Cartesian plane, 3-dimensional Cartesian coordinates allow us to display ordered triples as points in Cartesian space. The elements of an ordered triple corresponding to a point are the coordinates of that point. To locate a point in this 3-dimensional space, starting from the origin, we move along the x-axis a distance and direction specified by the x-coordinate. Then from that point, we move parallel to the y-axis a distance and direction specified by the y-coordinate. And finally, we move parallel to the z-axis a distance and direction specified by the z-coordinate. This determines the position of our point in Cartesian space. Another way to look at this is that the x and y coordinates locate a position on the xy plane just as in 2 dimensions, and the z coordinate specifies the point's distance above or below that position on the plane. Now that we have a way to visualize ordered pairs of real numbers as points on a plane, or ordered triples as points in space, the next step will be to create sets of ordered pairs which represent relations between different types of quantities. If the quantities can be represented by real numbers, then these relationships can be visualized in 2 or 3-dimensional space. We will do this in the next lecture by introducing the concept of a binary relation.
Nice. This guy should get a thumbs up. I'm not sure who disliked this video, man. This is really good. So anyway, so far what we've done is we've gone through what is called a degenerate interval, and it basically means you have a single element in the set and basically form an interval of that set, right? If it's unbounded interval, then you basically get an empty set because you got a single element with no boundaries whatsoever. And then if you have an interval with excluded elements in between those 2 intervals, you basically destroyed or basically change the definition of the interval. And in this case, because the interval includes all the values between the two points of that interval, in this case you will have to form some sort of a union and include only those intervals that bound the separating point. And then we got introduced to the Cartesian product, and before that we actually did the order theory. We talked about the ordered pairs. So the ordered pairs originate from what is called the Cartesian product. So in a Cartesian product, you basically combine two sets to form a whole new set, and a whole new different set. And for each pair, you combine the x and y axis, and you include those two elements together, and that's where you get the ordered pair. And it's very important in the Cartesian product to keep the orders in place, because changing the order changes the meaning, like completely changes the meaning. And this is called antisymmetric. And this is what is ordered pair means. So you have to always keep the order in place so that you do not jeopardize the meaning. And we've looked at the equivalence relation, and I think we should have looked into this phase before we went into the equivalence relation. So in the equivalence relation, it clearly says that the relation has to be symmetric, and in that sense, changing the order does not really matter for it. Does not really matter for the equivalence relation, and that what differentiates the equivalence relation from an ordered relation. And then we also have the binary relation. So the binary relation is simply a mere type of relation that connects two sets together, but with a given condition, of course. And that's something we could keep going. I think this set of videos really tell us a lot, and we could do more about this video. So the order theory is based on the binary relation. So the binary is the Cartesian product with the condition of both elements of A belong to the domain. So that's that. I mean, we could do more on this the next video. So thank you for tuning in, and have a good day. Yeah, before I leave, I think we can go with the videos. These videos are really good. We can keep going studying these. We can keep studying these, I mean. All right, have a good day.